So I'm on YouTube right now. I'm streaming this onto YouTube right now because at least one person can't be in class today because of the rain. Their car broke down. So I am now on YouTube. I'm also hopefully with this recording this so I can put it onto our Moodle page as well. Right now, Matthew.Michael11. You can also find it on the Moodle page. I have a link to it. What? So last time we talked about the different steps in order to do optimization, and we did two examples. We had the fence, and we had the fence, and then we had the distance to a point, right? We were trying to optimize it. Is it working? Cool. Last time I tried to do this, it did not work, so I'm glad it's working. Okay. I'm right now. Yeah. Huh? Yeah, I assume so. Yeah. That's yeah. So. Oh yeah, Matthew.Michael11 is going to become the newest big thing. Who's my favorite West player? So yeah, theoretically, I have my chat window up if people want to respond. We'll see if it actually does work. No, it goes to YouTube. It's on Moodle. Click on my name. It's not that weird. Other people. Anyway, rather than talking about all this again and again. Okay, so today's about is set aside specifically for optimization. Optimization. And we're going to be practicing with that today because optimization is one of those topics that a lot of people struggle with. And why is it going vertical there? So we're going to be practicing through a couple of standard and also non-standard examples. So I'll go through all the ones in your book, maybe some others. But before we get started, what were the steps again that we wanted to follow? Step one, define, or I said understand. But yeah, define the problem, understand the problem. So in that, what are we looking for? What are some of the things that we need to know to truly understand the problem? John. What are we looking for? Also, what else? Variables. What else? Constants. So oftentimes we might call these parameters. These are things that are defined by the problem. So oftentimes if we're dealing with the right triangle, remember we had the example of the ladder problem in related rates, and the ladder stayed a constant height. It just shifted. So that constant length of the ladder. It's not a variable, but I needed to know it, so it was a parameter. So numerical information. It could very well have to do with parameter, yeah. So these are kind of going back and forth between. Yeah. Okay, I think that's everything, unless somebody has something else. Okay, so the first step is remembering these 3 or 4 things, defining based on how you're defining it. What are we looking for? Variables, and what numerical informations can we turn into constants and parameters? 2, what was the second step? Draw a picture. As I keep saying, draw the pretty picture. Okay? I think that's pretty self-explanatory. You might need more than one picture, but you need at least one. Step 3. Hi, can I? So step 3, we've written down important. We know what we're looking for. We've drawn the pretty picture. Step 3, we do what? Okay. Well, notation could be useful here, but actually, yeah. Notation and equations. So variables very frequently will be, this notation will also very frequently be in step 1 as well, but it's really important if you haven't yet done it, is to put down if you haven't yet, you need to make sure you have all the information. You also need to define what the heck you're doing. Studies show that if you just write down r is the radius of your circle, you will do 1.5 times more likely to score a higher score. You'll score 1.5 times higher than you normally would. No. You will score. So if you normally score, say, a 4, you're more likely to get a 6. Huh? Right. But think about how often the difference between you getting an A at the end of the class and getting a B at the end of the class. Stuff like that. It does, and it's easy. All you had to do was say R is the radius of the circle. You get a free extra 50% of your previous score. Huh? It's not necessarily it's required, but by writing that down, your mind will make a connection that it normally doesn't. Yeah, it organizes the information in a way that helps you understand what you already know. Put it in the right box of information. Okay? So step 3 was notations and equations. Step 4 is what? Not quite. We're not quite there yet. Okay, that would be the equations. That would be step 3. Huh? I thought that was step 3. Just one. And so sort of what Avery was also saying, you both kind of got halfway there. So reduce equations, exactly as Alyssa said, to having only one variable. So if your surface area is dependent on R and H, step 4 will reduce surface area to only dependent on radius or on height, for example. So for example, if we talked last time about the can, a soda, right? You have to have a certain amount of soda in each can, otherwise people won't purchase your product. But you also want to reduce the size of the can to being the smallest possible size of surface area. Well, you can, but what I'm saying is this is currently dependent on both height and radius, whereas this will reduce it to the height will be a function of radius. It is, but it's sort of sucking it in. It's called projection. It's how much does this depend on this. It's projecting height into the radius domain. Okay? We have one equation with one variable. Now we can differentiate and plug in. Looking for maxes and mins. So yeah, so frequently it will be absolute maxes and mins. So you'll look for those critical points. You'll be looking for those endpoints. But also remember that you will frequently need to prove the extrema. This means you'll need to use first or second derivative tests. Okay? If I do indeed have a closed region, I could use the extreme value theorem. If I have an infinite domain, I'd have to use these first and second derivatives. Okay? So, define and understand the problem. So what are we looking for? Variables, constants, parameters, numerical information. Draw a picture. Draw the freaking pretty picture. Step 3, notation and equations. Turn them into that. Yes. Oftentimes that'll go into understanding the problem or the equations. That's where we start talking about, hey, x can be so big and how so small. Yeah. But yeah, that would kind of go in step 1. So let me put that there. Domain of variables. What? Not quite. Parameters are like saying the radius is 5. Parameter is a constant for a specific situation. Okay, so we've understand the problem, we draw the picture, we write down that in numerical information into an equation of variables. Step 4 takes those equations down to a single equation with a single variable, so that step 5 I can differentiate, plug the values in, solve for 0 to find my critical points, check the endpoints, and find my maxes and mins depending on what I'm looking for. Okay, question? Okay. Let's solve a problem. Here is the one question that every optimization student learns, because it annoys the heck out of you because it's a hard way of looking at it. It's not terrible, but it confuses a lot of people. An open top box is to be made by cutting small congruent. What's congruent mean again? All equal sides. Congruent, congruent means that they're the same. So congruent squares. From the corners of a 12-inch by 12-inch sheet of tin, and bending the sides. how large should the squares be cut from the corners to make the box as big as possible? An open-top box is to be made by cutting small congruent squares from the corners of a 12-inch by 12-inch sheet of tin and bending the sides. How large should the squares be cut from the corners to make the box as big as possible? Sometimes the first step might actually be to draw the pretty picture. So I have, how big is my piece of tin? What do I have to play with? A 12 by 12 piece of tin. And tin is gray, so I will make it gray. And is that a square? Nope, but it's close enough. Okay, so I have this particular square. Then I do what? I could, but what am I doing to this piece of tin? Cutting out the corners. Now, these corners, these squares are what? Congruent. And remember, congruent means they're equal. So that means, and they're squares, so they're all going to have the same side length. Now, if you want to call this S for side, I can do that instead. So you want X or S? X. Okay. So they're squares, so they have the same side lengths, and they're congruent, so they all have the same side lengths. And so I'm making these dotted lines to show where the fold marks are. So notice. Oh, my light's still on, so it's probably hard to see. Better? So notice, I have these dotted lines and I have holes here. We've done this before with cardboard, I think, most of us. So this means that this folds up, this folds up, this folds up, this folds up. So we're going to have, as I mentioned, an open top box. And how big is this again? It's 12 inches by 12 inches or 144 square inches, right? So notice how I mixed step 1 and 2 kind of together. These 5 steps are fluid. Use them. You don't have to be, oh, I need to write down all the numerical information right now. Draw the picture and start defining things. So I said I needed to define things, right? So X is what? Side length of cut out squares. What other things might be useful when I do this? Volume, right? B is the volume of the box. Why am I interested in volume? Why, Alex? Why am I trying to? Because it's saying how big it is, right? Isn't something big if it has a lot of surface area? You're right. I'm just being ornery. Yes, I am interested in volume. Surface area will be important. It could be because it's a surface area right here, but in this case, how big a box is isn't by saying how much am I using to make the box. I'm actually asking how big is the freaking box, right? So like dealing with box, that's connotations with volume. Okay? Other important bits of information that I've been given. Okay, yeah, and I put that down there, right? So 12 is length of side of uncut tin sheet. But say after it's been cut, this becomes my new side of the box, right? So how long is that, Alex? 12 minus 2x. Why not minus x? And this length? So what's the area of the bottom? So if this length is 12 minus 2x, and this width is 12 minus 2x, the area of the bottom is squared. What's the height of the box? X. Why? Because that's how much I cut out, so that's how much it can fold up. So notice I now understand the problem because I drew the pretty picture. I've written down the important bits of information. I know what variables I'm interested in. Remember, we also have domain, right? So if I have x, what's the smallest that x can be? Is it 1 or 0? Okay, why do you think it's 1? But theoretically, I could not cut anything, right? Because then could I cut only 1/2 inch out? Can I cut 1/3 of an inch out? So 0 would mean I don't cut anything, right? So it is possible. Ridiculous, I will grant you, but possible. What's the biggest that x can be? Which one? And why is it 6? They're going up from both sides, right? I can't cut something that's not there anymore. So at 6 inches, I cut 6 inches from the right. Oh, my right. 6 inches from my left. That means I've cut away all 12 inches, right? So let's make an equation. And I've already kind of done it. I have x and v, right? That's right, v in terms of x. V of x, which is the volume of the open top box in terms of the side length of the cut out square. I'm just being really ridiculous and writing everything out this first time. The volume is going to be what? 12 minus 2x, quantity squared, because that's the area of the bottom, times x. Okay. Now, how many variables are in this equation? 1. So do I even need to do the next step? Nope, I've already reduced it down to the number of variables I wanted to because of the way I set it up. Okay, not everybody writes it quite the same way as I do, so it is possible to have to do this next step. But I wrote it out this way to make it easier on us. So let's skip straight to step 5. Differentiate and plug in. Okay? So dv dx will be what? What rule am I going to have to use? Product rule. And please no. Please no. Yes. Yes, I could. Do I want to? No. Your book actually does distribute, but I'm not going to. Because no. Okay? I'll probably have to distribute after I differentiate, but it'll be easier. Instead of having a cubic, I'll have a quadratic. Okay? So if I need the product rule, that's derivative of the first times the second plus the first times the derivative of the second. Now notice they share common terms, right? What term do they share in common? So let's pull that out. 12 minus 2x, and I'm left with a 12 minus 2x minus 4x. Now that's a lot friendlier. 12 minus 2x times 12 minus, I think I heard it, 6x. Now that's a lot of really big numbers. So notice in the first product, and the first difference, 12 minus 2x, they share a common term of 2. So I can factor out a 2. That's going to become what? 6 minus x. The second difference, 12 minus 6x, as a factor of 6. So it becomes what? Say that again. 2 minus x. And 2 times 6 is? Booyah. So notice I have my derivative now. So now what? Look for the maxes and mins, and how do I do that? And where does it happen to equal to that magical, delicious number of 0? At 6 and 2. Hey, look, 6 was the endpoint of our domain, right? Now, I could plug those numbers in, say f of 0, f of 2, f of 6. This is 0, this is 0. Plug in 2, I'm going to get 2 times 12 minus 2 times 2 squared, or 2 times 12 minus 4 squared, 2 times 8 squared. 8 squared is, times 2 is, so 128 cubic inches looks like my answer. How can I prove it? I can do a chart. Do the second derivative test. Chart or second derivative test? I'll do the chart first, and then I'll do the second derivative test. And you shall see which one you prefer. So what are my my terms. So what's my lowest x value? What's my lowest x value? 0. So my chart starts from 0 up to 2. Then from 2 up to 6. And then that's it. So notice I do not include 6 on the right-hand side because what happens at x is equal to 6 for the derivative? It's not undefined. It's 0. So notice that's why I'm not including it in my setup. But now I have the term 2 minus x, term 6 minus x, and then my total derivative on that range. So from 0 to 2, 2 minus x is positive or negative? From 0 to 2, 6 minus x is, and a positive times a positive is, and because of that, the function is increasing. From 2 to 6, 2 minus x is what? Negative, right? Say plug in 3, 2 minus 3 is a negative 1. What about 6 minus x? Positive. Negative times a positive is negative, so that's decreasing. Therefore, what do we know? The first derivative test says this is the max. Okay? Second derivative test. So, this is dv dx, then d squared v dx is going to be 12, negative 1, 2 minus x, plus 12, 6 minus x times negative 1. Just a product rule. So that's going to be 12 times x minus 2 plus 12 times x minus 6. Or 24x minus 6 times 12 is 72. 2 times 12 is, so 72 and 24, or 24x minus 96. Or if you prefer, okay, so that's my second derivative, b double prime. And remember, what do I do with the second derivative on the second derivative test? Now they don't say that's looking for points of inflection. Plug what in? Plug in the critical point value. So that's 2 and that's 6. So if I plug in 2, I get 24, 2 minus 4, which is negative 48, which is definitely negative, which means what, Alex? This means it's a max according to the second derivative test. And if I plug in 6, so that is a min, which we already know, right? Does this. So either way you prefer, notice it was about the same amount of work, right? Depending on how you want to do it, that works. It was a kind of 50-50 split, so I went with both ways. So what is my final answer? No. What was the question? Remember, the whole point of this was so how large should we cut that with 2-inch sides? So 2 could be the right answer depending on how you framed it. So the max volume is 128, but in and of itself, that's not what we're looking for. We're looking for how big should the squares be cut. So you could have also said you need to cut out 4 square inches from each of the corners. Cut 2-inch by 2-inch squares from corners. Okay? So note, I drew the pretty picture. On the pretty picture, I wrote down all the numerical information. That's why it's so useful. You can actually synthesize all the information onto the picture. I wrote an equation using the variables that we defined, took their derivative, found critical points, found out what their volumes were, and using that, I proved that it was a maximum at x is equal to 2 because I either used the first or second derivative. Okay? Questions? We're good? Question number 2. Okay. You too. Sound familiar? I've been using this example. You've been asked to design a 1-liter can shaped like a right cylinder. That's a big can. What dimensions will use the least amount of material? Okay, so I can either write down the numerical information or I can draw the picture. Which one you want to do first? Picture? I heard picture more commonly. So it's a right cylinder. So that's just a can. So hello, Gray. I have a can. Now, what are some important variables that are defined by the can? Right can. What? What? Okay, 1-liter volume. So volume is equal to 1 liter. Okay, what else? What variables? What? Surface area. What am I doing with surface area? That's what I'm looking for. I want to minimize surface area. But what are some what are some other variables I might need? Radius and height. Volume of can, radius of can, height of can. Now, a liter. That's going to make things really annoying when I deal with dimensions, right? Is there a way that I can turn a liter into some cubic length measurement? Cubic centimeters. 1 liter is equal to 1,000 cubic centimeters. Because it's metric, liter is a volume measurement, but if I'm going to be dealing with dimensions, I'm going to need a length measurement. And liter won't. It's actually not. A liter is 1,000 cubic centimeters. Right, I'm saying 10 meters is not a liter. It's not. Okay, remember, 1 meter is equal to 100 centimeters, right? So if I take centimeters and cube it, that's going to be 100 cubed in 1 cubic meter. So that's 1, 2, 3. So not even 1 cubic meter. Okay, 1 decimeter is equal to 10 centimeters. Sure, it is a cubic decimeter, but nobody uses decimeters. But yes, because it's not useful, it's one of those things that it's much easier just to use centimeters and meters. Just not. Yes, we technically could, but we typically don't. For the most part, you probably won't need it, but occasionally it might become useful. Okay. Have I written down everything numerical that I have available to me? Not equations, just numerical information. Yes. I've also drawn all that I can at the moment, right? So step 3 is what? Relate some equations, right? So how do I calculate the volume of this cylinder? Pi r squared h. And guess what? What's that equal to? 1 liter, or as I prefer it, 1,000, 1 liter or 1,000 cubic centimeters. Okay. Any other equations that I can deal with? Surface area. So look, how many surfaces am I dealing with here? 3. Top, bottom, and the side, right? You're looking at the top, which you normally peel off. You have the bottom, which holds everything in, and then you have the label. So how much area does the top have? Pi r squared, right? It's just a circle on top. What about the bottom? Okay. Now, what about the label? Length, which is going to be h, so it's times the circumference, right? 2 pi r. If you don't believe me, remember we have a can, and we have a label on it. and I unwrap it. And it's a rectangle. The length is h, and then I have circumference around the circle. Okay? So surface area can instead be written as 2 pi r squared plus 2 pi rh. And that is what I am trying to minimize. But here's the thing. How many equations do I have? How many different variables do I have? Two. Volume is remember I said parameters, right? In this case, v is the parameter, so it's not a variable because the volume is never changing. Now the radius and the height can change. Now I want to talk about domain. Now clearly R and H are going to be our variables and SA is what we're trying to minimize, right? So what's going to be the range of R? Thank you. Okay. So let's say we have this shape, right? If I could start squeezing my can, what's the height going to do? Boom, right? Because remember, I have to have a volume of 1,000 cubic centimeters. Now, suppose I keep squeezing. Can I ever make my radius 0?
Yes.
No, because what happens if I squeeze it down to 0? What happens to it? It goes into an infinite line, right? And this doesn't make sense. I can't make a radius of actually 0. It approaches 0, which means instead of a hard bracket, I'm going to have parentheses. Soft bracket, which is a parenthesis. Okay, now let's go to the other side. Let's say if I take my can and I squish it, the radius will get bigger and bigger and bigger, but not quite up to infinity. Similarly, the height can go from 0 to infinity, not including the endpoints. So let's have fun. Because in this next step, I need to do what? One variable, one equation. Is there an equation I can get rid of? Yes. I could move this under there. No, why was H a good choice, Avery?
Because you don't have to square it.
Because if I did the same thing, it's the right equation, but if I used R, I would have had to use an annoying square root. Is it possible to use it? Absolutely. Do I want to? Absolutely not. So what do I do with this marvelous H is equal to 1,000 over pi r squared? Plug it in, plug it in. Dated references all the time. Plus 2 pi r 1,000 over pi r squared. Hey, look, we have some cancellation. What cancels? Pi's and an r. So I'm going to be left with the surface area is equal to pi r squared plus 2,000 over r. Now, is that an equation with one variable? Variable of radius. So am I ready to differentiate? Sure. So let's differentiate. dSA over dr is equal to and what do I want to do with it? Solve for r when this is equal to 0. So 4 pi r is equal to 2000 over r squared. So r cubed is equal to 500 over pi. In other words, the radius is equal to what? The cube root of 500 over pi. Okay? In this case, I strongly suggest us not to use the first derivative test. We okay with that? So at the second derivative, the derivative is equal to 4 pi plus, not 2000, 4,000 over r cubed. Now, what was the domain for r again? 0 to infinity. In other words, r is always what sign? So what is this equal? If r is always positive, what's r cubed? And 4,000 divided by a positive number is plus 4 pi is. So guess what? The second derivative is, no, it's actually negative. I'm kidding. And because the second derivative is, all of you were like, wait, what just happened? No, so it's a minimum. Okay, questions? Now what am I looking for? Do I have enough? No, I only have one of the important bits of information. I have r is equal to the cubic root of 500 over pi. In order to keep going, what do I need? What do I need to finish? Plug in r for h. So h is 1,000 over pi r squared, right? Now I could just plug it in, which I will. But you'll notice something interesting happens. A nasty, nasty, nasty nasty complex fraction. Now pi over pi to the 2/3 power is what? Pi to the 1/3 power. So I left with pi to the 1/3 power on bottom. Now I have 1,000 over 500. Wow, that was bad. 500 to the 2/3 power. Or 500 over 500 to the 2/3 power times 2. So that's just going to be 2 times 500 to the 1/3 power, right? So that's 2 times the cubic root of 500 over pi. But wait a minute, what's r equal to?
Oh, wow.
Right? It's not important per se, but it turns out that the height will be 2 times the radius. Because math. In this case, the optimized case is that the height is 2 times the radius. I can't tell you anything beyond saying because math. Okay? Questions? No questions? Okay? Bad. A rectangular page is to contain 24 square inches of print. The margins on the top and bottom are to be 1.5 inches. The side margins are to be 1 inch. So that's left and right. What should the dimensions of the overall page, not the inner text region, but overall, what should those dimensions be so that I use the least amount of paper? Go ahead and give it a shot. And yes, this has shown up on a common exam before. And I know there's one person watching this right now. Feel free to comment and ask questions if you need to. Solve it during the comments, okay. Oh, I think I did another one of these videos last year. I have another video that I did the exact same thing, only we had class canceled. So I was by myself. It was snowing outside. It was actually not this week, but the next week. And I canceled class, so we didn't have to come to snow. But I told everybody they had to get onto YouTube, and I watched my class watch it all at once.
That's cool.
I liked it. Yeah, it worked. Not everybody was actually on YouTube, but it was close enough. But there's another video of me doing these problems at my wife's grad school. I set it up on a big whiteboard. So if you want to check that out, that works too.
Oh, that's a valid point. I didn't put it on the website.
Apparently, I with every other class except for yours, I did not put the YouTube site on your class. But if you looked it up online, you should notice up on Google that it does show up. So let me put it on right now. Okay, it should work now. Find it? draw a picture, numerical information, define some variables, relate the variables, reduce down to a single equation, and solve. There are two ways to solve this problem with equations that will be slightly different from each other. Depends. So this question is an example of when you need to be very, very, very careful on how you define your variables. Because how many different areas are we solving for? Two. We have two areas we're dealing with. Inner area and an outer area. Be very careful.
So the 24 inch square thing is the subcontinental.
Correct. That's why it says a rectangular base is 24 square. Not is 24 square. Otherwise, we're done. It's a different problem entirely, which they've also done, but they give you the overall case and want to maximize the amount of variables. It's a different, it's called the maximum problem. You can reverse the problem. Yeah, very simple. The top and bottom, it margins are each how big? And the sides, how big are the side margins? One each. Okay. There you go. Possibly. You're saying the inner region, the inner area is the other? Sure, but what's the inner area? You solve for one of the variables? See, a lot of people kind of stuck after they set it up, and they're like, so now 50 copies, boom, I have the answer, right? You actually have to do that. Most of you look like you're doing the right thing, you just plug it in. Okay. So which one is it? Oh, sure. What's the inner area? 4. So 42 text this way. How many text this way? 24. So this 24, but there is a smaller region. Let me double check. Just the smaller region. You can't. Not quite. Okay. We have 4 minutes left, so let's answer this question in 4 minutes, shall we? So, I have this region, and I have an inner region. Now, this margin is 1.4, 1.5. This is 1.5. This is 1. This is 1. I know that the inner area is equal to 24, and I know that the outer area is going to be what I'm looking for, right? I'm trying to minimize that. So that means that red area, inner area, is what I'm going to solve for. So let's make that as simple as possible. So make x equal to the length of the inner region, and I just lost my internet. Really, length of the inner region with y equal to the length of so this is the horizontal length, this is the vertical length. And this is useful because I'm solving 24 is equal to x times y, right? I could have done the opposite, but then I would have had 24 is equal to x minus 2 times y minus 3, which is fine. But it means at the very end, I know that x and y are not my interesting variables. I have to remind myself that x and y are not what I'm solving for. I'm solving for x plus 2 and y plus 3. So that means my overall area that I'm solving for, my outer area is going to be defined as x plus 2, y plus 3. And since I know that 24 is equal to x times y, and I don't like y, let's solve for it and get rid of it. So this ends up becoming x plus 2, 24 over x plus 3. And expand. And I will get 30 plus 2x plus 72 over x. It's equal to the outer area. I let you figure it out yourself, but it does work out to be like this, because I'm now in a little bit of a rush. Take the derivative. I will get 2 minus 72 over x squared. Set that equal to 0. X is equal to plus and minus 6. But am I actually interested in the minus 6? Doesn't make sense. So remember, y is equal to 24 over x. That becomes 24 over 6, which is 4. Now, since my derivative was equal to 2 minus 72 over x squared, my second derivative test would also be an excellent choice. Take the second derivative, I get positive 144 over x cubed, which is always going to be positive, so I'm going to have a min at 8 inches by 7 inches. So Alex, you were right. I misread my notes here. Okay? And that's a wrap. How did I go from here to here? I expanded. Okay? Have a lovely day.